All right. Can we agree that the center of mass is going to lie along this line? Right. If we're looking for the y direction of the center of mass, then it's got to lie along this line. Now, one way of doing this would be to just do this in 3 different directions, right? Meaning, as I said yesterday, we could find the balance point, and based on symmetry, that's probably where it is, right? Just symmetrically. But you realize that there's only 1 pin in this row and 2 pins in this row and 3 pins in this row and 4 pins in that row. In the y direction, if I start with this as my reference, then I could go by rows. So I know it's got to lie along this line. So 4 pins are going to contribute to the mass all the way in the back. 3 pins are going to contribute to the mass in that second row. 2 pins are going to contribute in that third row, and only 1 pin contributes to the mass in the first row. Based on using this function, I could do, well, m is just going to be m for 1 pin, and it's a distance 0 away from the reference point. That's the first pin. The second second row, mass of 2m, because there are 2 pins, a distance x away from the reference point. Next row, what's that mass? 3m. 2x. There we go. One more, right? 4m, 3x. On the bottom, what's the bottom? 10m, 10 pins. The answer shouldn't end up having mass in it, but mass contributes to the answer. So the top's going to be 2mx plus 6mx plus 12mx, right? So let's see, 2 plus 6 is 8, 8 plus 12 is 20, 20mx divided by, 20mx divided by 10m. Bless you. Looks like I get 2x. Where does that put it? 1x, 2x. Right there. Now, I don't want to play too much with the whole idea of center of mass. There's not a lot that we have to kind of know about it, but I want you to be able to do this. Because the next thing we're going to have to do is, and we was here, but it's as long as you can do this semester's version, we'll be okay. To speak to the word momentum first, and maybe try and define it. My favorite definition is one of those definitions that I tell students to know, even though it's a useless piece of information. I say this not to be me. I do this a lot, I think. We already have difficulty with vocabulary words. My favorite one is inertia in mass, because it's such a hard concept to develop. Inertia is an object's resistance to changes in motion. I've been saying it all year. And we measure inertia by measuring something's mass. Momentum is inertia while moving. or inertia in motion. You see, when something begins to move, its inertia increases. The more something's moving, the more inertia it has, the more difficult it is to change its motion. So when things are moving, they increase their inertia. So we use the word momentum often to describe things socially too, that there can be social momentum. Something going viral is social momentum. It kind of has a momentum. It's difficult to change once it starts. You guys know what I'm talking about, right? When something goes viral, it spreads quickly. Well, it has kind of what's called institutional momentum, and that's being propagated. Physical momentum is just a product of mass and velocity. And of course, because it's physics, we use a lowercase p. I have no idea why. But that's the letter used for momentum. M was already chosen, I guess. So we just went a couple letters to the right. Momentum has direction. It takes the direction from the velocity. And it has no name for its unit. It's kilograms meters per second. So no name there. Don't confuse momentum with kinetic energy. They're not the same. They tell us different things. Kinetic energy is the energy of an object. That does not tell us anything about its momentum. Although they look similar, understand momentum has direction. That's an important distinction. If you're going to write anything down today about momentum that I'm not going to write down, put down that momentum has direction. Now, I said to you a minute ago that the word impulse means change in momentum. I want to be really careful here. Change in momentum. So P final minus P initial. And so impulse has the same units as momentum, because it's just a change in something's momentum. This can be a three-dimensional change in the object's momentum. So a baseball being struck by a bat receives an impulse, right? It was traveling in one direction with one momentum, and then suddenly is traveling in another direction with a different momentum. There was clearly an impulse provided to the ball from the bat. Now, because of Newton's third law, the bat also received an impulse from the ball. So remember, when we talk about impulses, just like when we talked about work, there's reciprocation in all of this. So if you've ever boxed before, anybody ever boxed? I'd use other types of fighting, but boxing is becoming less and less relevant. I talk about the causes of an impulse. We are generally talking about things that happen very quickly. There's usually not enough time for the object to have any meaningful change in displacement. So we wouldn't describe the time that the ball is in contact with the bat as having much of a change in location, would you? Or even a tennis racket and a tennis ball. Now, a car accident, you're likely to have the car moving while it stopped. You understand that the first part of a car accident doesn't take place with you at all. It takes place with the two cars beginning to crumble. A 30-mile-an-hour car accident generally destroys the car. The whole outside of it falls apart. You've seen what car accidents look like nowadays, right? A few of you have been in them. Bumpers are gone, bumper covers are gone, the car's all completely crumpled. Have you ever seen a car accident from the 1940s and 50s? There might be a dent in a bumper, but probably not. Cars didn't have crumple zones back then. The car looked perfect, which means your part of the car accident began at 30 miles an hour. But if you're in a modern day car, you've already been slowed down because the car has begun to crumple around you. So by the time you hit your restraint systems, you're already traveling slower because the car has absorbed and begun the portion of the impulse. You see, one of the major differences is a dashboard will stop you in about 4 to 6 milliseconds. And the seatbelt will stop you in about 100 milliseconds. And an airbag can stop you in like 500 to 800 milliseconds. Now, take a look at what that means here. change in momentum. Let's see, we'll pick one of you guys. An average sized person here, we'll say upper torso. So if you're, say 140 pounds, upper torso, maybe half of that, 70 pounds, divide that by, let's say we're talking about a 35 kilogram upper torso. Change in momentum of that upper torso is going to be P final minus P initial. It's going to be 0 minus 35 times 30. Well, 30 miles an hour, I probably should put that in meters per second. So 30 miles an hour is about 16 meters per second. No, I'm sorry, 15 meters per second. I think it's 14.2, but we'll just do 15. It's a nice round number. The right side, well, the effect is you're going to be stopped, right? The impulse is the same, whether you're stopped by your seatbelt, the dashboard, the airbag, or the street, right? The impulse is the same. You're going to be brought to rest. Understand that the effect is the same. If I drop the cup on the ground, the impulse experienced by the cup is the same. The cup's going to be stopped by the ground. Everybody following along? This side decides how that happens. So with the airbag, it's up to about, let's just do it in the middle, because it's like 500 to 800 is what I looked up. We'll do it in the middle. 500 to 800 milliseconds will be 0.7, 0.5 to 0.8. Of course, seatbelt dash which one do you want to use? You see why, right? You see what's going to happen here, right? If I can increase how long it takes to stop, I can decrease how much force is necessary to stop you. We're talking about a car accident, you're going to be stopped one way or the other, right? You're going to be stopped one way or the other. You can decide how long it takes to stop. Now, I would argue that sliding down the street takes the longest to stop. But that's probably not the way you want to stop, right? Because you leave a long meat stripe across the ground. That's not good for anybody. So we prefer not that. We want to control where this occurs. That's also, there's more to it than just this. But you see quite clearly that if you want to reduce the force, you increase how much time it takes to stop. Now, we do more than just that. If you look at the way seatbelts are designed, they're designed to also act on specific parts of the human body that are stronger and can take it. We don't wrap the seatbelt around our neck, we wrap it around our shoulder, chest cavity, and then mount it to 2 points that have some of the biggest bones in our bodies. That's why they are the way they are. It's not accidental. And of course, we could all have 5-point harnesses in our car like we do for little babies, but we don't do that anymore either. They did for a time. Right? We're going right back to this cause and effect. The players, they already work out. They're already elite athletes. They swing the bat, and the bats are heavily controlled. So if I want to change the game, knowing that most of the players can only swing so hard and apply a certain amount of force to the ball, I might want to manipulate the game by changing how long the ball is in contact with the bat. So you make the ball a little squishier. You change how long the ball is in contact with the bat, and that gives you the effect of a larger change in momentum. That's how people cheat in baseball, right? To cheat in baseball, you take the bat, you hollow it out, and you fill it with a softer wood. And then you carefully apply the cap back to the top of the bat so all the grain matches up. And that way, you have to be careful when you do this because you want to make sure that it balances in the same point, because bats are inspected before they go out in the field so that they're all regulation. You do it just right, though, you can make your bat a little bit softer. Make sure the bat boy gives you that bat. That's your bat. And then you go out there, hit the ball stays in contact with the bat a little bit longer. Ball's going to go further. That's cheating, though. So when baseball wants to change something, the commissioner changes the ball. Everybody still has the same rules for the bat. It works in tennis, too. The balls have changed a bunch. It works in golf. That's why golf balls have to be regulated as well, to make sure everybody has a level playing field for these games. But in all cases, you understand what's being manipulated here. What is softness? Well, it's right there. It's in this. So you see why the cup doesn't shatter on the carpet, right? The carpet allows the cup to take longer to stop. That reduces how much force the cup's going to experience. But if I drop it on a hard floor, it's going to stop in a very short amount of time. But you do understand in both cases, the amount of time is relatively small. That's the thing. For all of these, impulses tend to be around problems where the time is very small. Doesn't have to be, but it tends to be. Now, I do need to take a brief moment to talk about this for a minute because this is AP Physics C, and you guys are in a position to understand more things. First, look carefully at this. We have vectors involved here. The direction of this force is in the direction of the change of momentum. I want to be very careful about this. If a ball is coming this way and you strike it with a bat, it's now going this way, it's pretty clear that the force that would be required to do that would have to be in this direction, right? You guys see that okay? Now that one's obvious. In this case, the force is clearly in the direction of the final momentum of the object. Is that one pretty easy to understand? You see that so far? What makes it more difficult is understanding that it's not always about one of the directions, or at least it's not as obvious. What if the puck is going this way, and in hockey, after it's been struck by the stick, the puck's going this way. Now, do it this semester, but we're going to have to find things like the center of mass of something like this. Something that's not nice and symmetrical and uniform. And this is going to be harder. And we'll need a way to do this. It's going to end here. All right, so this is second semester's version.